the history of Antarctica and its effect on climate change, and how climate change will affect us. So we've had one webinar so far with Tim Nash covered it's the general picture, and now we're getting into a bit more detail with Holly, who's going to cover ice cores and where that evidence has come from. Hand over to on behalf of the New Zealand Antarctic Society. So I'll hand over to Linda Kessel, who's the president of the Antarctic Society, and she'll introduce our speaker for this evening. So Linda, over to you.
Well, hello everyone again. Thank you, Ken, and welcome, Holly. I'd like us to welcome Dr. Holly Winton, who is, I understand it, from Victoria University in Wellington in the Antarctic Research Centre. And you have or are already still working with GNS and Nancy Bertler on ice cores and looking at the predictions for the Southern Ocean, I believe. Yes? So the title of the talk tonight is, as I understand it, Frozen in Time, Unlocking the History of Ancient Ice. And obviously this is all about ice cores, which archive and record detailed signals, it says, about the atmosphere and environment at the times the snow actually fell, which I thought was quite curious myself. I didn't realize it was when the snow fell that you were looking at. And that these ice cores are predominantly drilled, obviously, through polar ice caps and contain climate information over seasonal and millennial time in terms of the scales of time, and obviously looking at temperature and carbon dioxide levels and records. So welcome, Holly. On behalf of the Antarctic Society, we've sort of moved from the 20th century to the 21st century by running these seminars, and so in many respects thanks to COVID. But I'd like to also welcome Antarctic Society members. If you're online and watching these webinars, fantastic. If you are not a member of the Antarctic Society, you can go onto our website, the New Zealand Antarctic Society.org.nz, and for $75 a year, you can receive 4 magazines, Antarctic magazines, and you also get to go along to various events quite apart from these webinars. So I would encourage you to do that. It's a wonderful networking of people who are interested in the Antarctic. You don't have to be an Antarctican. An Antarctican is someone who's actually been there, and you get the certificate and all sorts of things. So without further ado, I'd like to hand over to you, Holly. Welcome.
Thank you, Linda, and thank you, Ken, for the warm introduction and the opportunity to talk to the Antarctic Society. It's really great to connect with you all. I have been overseas for the last 7 or 8 years working on ice core projects in Australia and the UK, and now I'm back in New Zealand as a Rutherford postdoc, working with the New Zealand team in the Ross Sea region of Antarctica. And in the first webinar, Tim Nash talked about climate change over the geological record. And of course, one of the really key pieces of evidence there comes from the air bubbles in ice cores. So that's what I'm going to talk to you about today. I'll share my screen. There we go. So yes, the title of this talk is Frozen in Time, and I'm going to talk to you about how we unlock the climate history from ice cores. So ice cores are most famous for their temperature and CO2 records over glacial and interglacial timescales. So I'm going to really focus on that today, but also wanted to give you a bit of a flavour for some of the other really cool information we get from ice cores and some of the new exciting developments we're doing here in New Zealand. But first, I'll give you a bit of an introduction to what an ice core is. So there's a nice picture of an ice core inside the drill. And the ice over Antarctica and Greenland is made up of many annual layers. So you can see all these nice layers in this photo here. And as the snow falls each year, these layers build up. with the oldest layers at the bottom and the youngest layers at the top. And the process by which the snow turns into ice is called vernification. So this here is vern, and this is where the air pockets between the snow grains are in contact with the overlying air. At about 100 meters depth, these air pockets actually close off. They close off to air bubbles and they're no longer in contact with the atmosphere. So that is our archive of the atmospheric composition. Here is a photo of a 2-meter snow pit. So I guess some of you have been to Antarctica, perhaps you've walked out onto Windless Bight, and this is actually what you're walking on top of. So you're walking on top of all of these beautiful layers in the snow. And of course, as ice core scientists, we're interested in drilling through those layers to bring back a history or a timeline of how the atmosphere and environment has changed. So what is in an ice core? So not surprisingly, ice cores are mainly made up of oxygen and hydrogen, and we're interested in the isotopes, or the ratios between the isotopes, as that is what gives us our temperature records. In the ice, we also measure impurities, so ash from volcanic eruptions that travels through the atmosphere and is deposited on Antarctica. We measure sea salts, we measure atmospheric dust, we can measure smoke particles from forest fires from Australia, for example. Of course, there's the air bubbles that have an archive of greenhouse gases. And then we're also interested in looking at the physical properties of the snow grains themselves. So predominantly, today I'm going to talk about Antarctic ice cores. But ice cores come from anywhere really there is glacial ice. So Greenland, the third pole, and even some mountain alpine glaciers. In terms of paleoclimate records, ice cores have pretty good dating. They're pretty reliable and very detailed. So I thought I would just give you a bit of an overview about how we actually date the records. So the first thing we do is something called annual layer counting, and we use this for the top few thousand years of the ice cores. And what we do is we pick up a seasonal signal, such as temperature, and we basically count back all the winters or all the summers. Today we speed that up using machine learning, and we can constrain our dating using fixed time markers. Here's a really nice picture of a volcanic horizon with a known age. In the deeper layers, we need to use some ice sheet modelling to work out the age of those layers. So what are the key science questions we can use ice cores to tell us about? So we're looking at climate variability over a range of scales from 2,000 years, 40,000 years, going back to the oldest ice project, which is in process at the moment, trying to find a site that has ice over 1 million years old. How do we drill them? So depending on how deep we want, we can use a hand drill all the way down to a deep drill. And then how do we analyze them? So once we have our ice core returned from Antarctica into the lab, we cut it into various sections. We use continuous flow analysis. So this is where you have a stick of ice and you actually melt it on a heated melt head. And all of that melt water goes through various channels, pops out in our warm lab where we send it to various instruments to measure the chemistry in the ice. And this is what some of the data looks like. We then process that data, we date the core, and there may be some particular time periods we're very interested in. So we may go back, cut some more ice and do some further analyses. And then at that point, we end up with our record of chemistry through time that we can interpret. So it takes a bit of effort to get these climate records from ice cores. just to give you a very, very brief history of ice core drilling. It's a very young science. It really kicked off during the IGY, 1957 to 1958, the International Geophysical Year, and it started in Greenland. And you can see this picture, there are a number of ice core sites in Greenland, and all of these sites were drilled to try to recover ice that goes back to the last interglacial. So Tim mentioned this time period in the last webinar. It's the last time in the Earth's history that temperatures were similar to today. However, none of the records could provide a reliable climate record beyond about 120,000 years. So scientists looked to Antarctica. That, combined with the Milankovitch theory of the ice ages, really prompted glaciologists to extend the ice core record beyond the Greenland record, which just really goes back to this last glacial period. So the first ice core in Antarctica, which managed to recover a full glacial-interglacial cycle, was Bostock. You can see from this image here that it took many, many attempts over many, many years to be able to recover the core from Bostock. That's because of technical difficulties and the drill getting stuck. The oldest ice we have is from Dome C in the centre of Antarctica. It's a European consortium project, goes back 800,000 years. Okay, so now I'm going to talk about temperature and CO2 over glacial-interglacial time periods. This is probably the most key information that has come out of our ice core records. So how do we get our temperature from Antarctic ice? So we use these stable isotopes of water, and we are interested in looking at those isotopes and the ratio between those isotopes, as that can tell us how temperature has changed in the past. So here you can see some wiggles, and these are related to temperature, summer and winter temperature. I'm then going to show you the full water isotope record from the oldest ice core in Antarctica, so that's Dome C. So here you can see that temperature, here we are today, and this is going back 800,000 years. You can see that temperature varied a lot in the past. It goes up and down and up and down. So what did CO2 do? It's a nice image of the air bubbles in the ice core. And I'm just going to show you a quick video of dropping a piece of glacial ice into water. So listen out for the crackling and the bubbling of the release of the air from the ice. Okay, so this is what the CO2 record looks like. It's on top of temperature. You can see that as one goes up, the other goes down. So when it's cold, temperature is lower, CO2 is lower, and vice versa. You can also see that there is a really large range in temperature, 10 degrees, between what we call glacial time periods. So these are the cold times. These are when ice sheets were much faster than they are today. Sea level was lower. And there's a 10-degree temperature change between this time and what we call interglacial. So that's where we are now. These are warm time periods. Sea level rise was higher. Temperatures were higher. The other thing you can see from this graph is that there are cycles in the temperature and CO2. So they go up and down and up and down and up and down. And you can almost mirror these cycles on top of each other. And that is due to these Milankovitch cycles. So that's the cycles in the Earth's orbit. Tim mentioned these last webinar. And it's the solar insulation that is really controlling temperature between these glacial and interglacial cycles. And there are 3 of these cycles in the Earth's orbit, and each of those is imprinted in our temperature record. So here is, I have just zoomed into the last 150,000 years, and you can see this nice 100,000 year cycle imprinted. Let's now take a closer look at this time period. So this is what we call the last interglacial. Temperatures were similar or a few degrees greater than today. Sea level was similar or greater than today. CO2 was about 280 ppm. Now let's zoom into the last 1,000 years. CO2 was fairly constant. And so this is CO2 in the red circles from the ice core, and in the green are actual measurements we have made. So these are increasing, we know this. CO2 today was around 420 ppm, and future predictions of CO2 are off the chart. This will probably be covered later in this webinar series, but just so you can see that we are really above the CO2 records seen in the past ice core record. We also see that during this last 150,000 years, the fastest rate of change took 1,000 years to take place, compared to only 20 years the same rate took place in our recent time. Okay, let's now focus on this more recent time period. So here is zoomed in the instrumental record of CO2. The longest record comes from Mauna Loa, starting 1958. Also plotted here is the record from Halley Station, Antarctica. This picture here is of the CAS lab at Halley Station, which has been measuring CO2 for a number of years now. And then if we add on here the CO2 and the ice core bubbles, we can see this is really nice overlap between the instrumental record and our ice core data. So we're pretty confident we're doing a good job here of measuring the atmospheric CO2. This bottom graph, you can see all of the CO2 measurements from ice cores over the last 2,000 years. So there are 5 different ice cores here that span all of Antarctica. But we don't fully understand how the climate and carbon cycle work over the last 2,000 years. But one way to help us, we can characterize the carbon source. So we can actually measure the carbon-13 isotopic composition in the carbon and the CO2. And that carbon-13 has very broadly 2 distinct reservoirs of carbon with a different isotopic signal. So one is the ocean and the other is the terrestrial biosphere. So when we measure and fingerprint the source of carbon in the ice cores, we see that there is this strong decrease at the same time that the CO2 rises. And this is due to the increase in fossil fuel burning. This carbon signature is characteristic of fossil fuel burning. So there's another piece of evidence from the ice core record. Okay, so what was temperature doing in Antarctica over the last 2,000 years? In the middle here is a picture of Antarctica, and it's divided into various regions. And between this period 0 to 1900, Antarctica was cooling. And then each of these figures around correspond to a particular region in Antarctica. And over the last 200 years, 3 of these regions were actually warming. So one here is the Groningen-Maudlin Coast, the Antarctic Peninsula, and West Antarctica. And in actual fact, West Antarctica really stands out. The warming of the last 2,000 years is very different to the rest of the record. And what we see is East Antarctica is really the last place in Antarctica to be responding to climate change. Okay, so we've seen how CO2 and temperature have varied naturally in the past, and we've looked at the anthropogenic forcing over the last 2,000 years. Also wanted to tell you one more really key piece of information from ice cores, and that is ice cores have shown us that abrupt climate change can take place. So we are now looking at the temperature record from Greenland. Here we are in the Holocene, and we're looking at this glacial time period. And this looks very different to what we've seen from Antarctica. We see this rapid warming followed by a slower cooling. Rapid warming followed by a slower cooling. And there are many of these events during this glacial time period. These are known as DO, or Danskard Oshka events, and these are rapid, fast, and large changes in climate. They can occur over a decade. And you may be wondering, okay, is this localized to Greenland, the Northern Hemisphere? But when we look at Antarctica, we actually see that this is more of a global change. So in Greenland, when it's cold, Antarctica is actually warming and vice versa. And this is known as this bipolar seesaw. So there is this distribution or redistribution of heat between the Northern Hemisphere and the Southern Hemisphere. And the mechanism that distributes the heat is actually through the ocean. It's this great ocean conveyor belt. How does that work? Well, around Antarctica, where it's very cold, in the ocean, cold, dense, salty water is produced that sinks, and it actually is driving the circulation of water around the world. Those currents re-emerge in the North Atlantic as warm currents. That's what heats Europe. And during this last glacial period, it's thought that the sinking, this is when we had large ice sheets and the water around them was freshening. And so this is sort of stopping the dense water sinking, and this ocean conveyor belt is essentially switched off. So it's the switching on and off of this heat distributor that is causing these abrupt climate change events in the past. Okay, I wanted to talk about the oldest ice. So this is the next big ice core project. We talked about that temperature varies around the world on a cycle of around 100,000 years. We call this the 100K world. However, ocean records show that around 1 million years, this changed to a 40K world. But our ice cores don't go that far back. They only go back 800,000 years. So our aim is to drill an ice core going back 100 million years, 1.5 million years, to see what CO2 was doing during this transition. A site has been chosen, ironically only 50 kilometres apart from the Dome Sea site. And this was quite a challenge to find a site. As you can see, here is the topography of the rock under the ice. This is a 10-kilometre scale and sort of quite mountainous, and there are actually pockets of water. So to find a location that had ice at the bottom that was about 1.5 million years old is quite a challenge. Okay, so what are the ice core perspectives from the last 800,000 years? I hope I've shown you that ice cores are the only archive of ancient greenhouse gases. Carbon dioxide in the ice core record has never exceeded 300 ppm. The past 2,000 years provides an important baseline to put the recent carbon dioxide and temperature rise into context. Carbon dioxide is now well above the natural ice core range and increasing at an unprecedented rate. We have seen abrupt climate change occurring within decades. Okay, I wanted to give you a bit of a flavour for some of the other really cool information we can get from ice cores. Some of these things include atmospheric pollution, windiness, forest fire burning, UV and ozone radiation, sea ice, marine microbiota, and changes in ice sheet elevation. So in this schematic here, we have transport of mineral dust and ash of fire particles and atmospheric pollution. These get transported in the atmosphere and get deposited in our ice core. We also have a marine component. So we have particles emitted from the surface ocean, from marine microorganisms, and from sea ice. And these, again, all get transported in the atmosphere and deposited at our ice core site. So I'll just talk about a couple of these examples. So in 1911, when Scott and Amundsen raced to the pole, they thought they were going to a location that humans had not touched, that humans had not reached before. In actually fact, they were wrong. And atmospheric pollution beat them to the pole by over 20 years. So here's the example of lead. In about 1855, there was this massive jump in lead pollution. This isn't just observed in one ice core, this is observed in ice cores all over the Antarctic. There was a bit of a dip during the Great Depression, World War II. This then increased again and decreased as a result of unleaded petrol. But what you can see is that despite these efforts, lead still persists in the atmosphere. This large spike in 1885 has been attributed to about one source. So this is lead pollution in the Southern Hemisphere from Broken Hill in Australia. The other example is sea ice proxies. So as you heard from Tim, and we will hear in a future seminar, that sea ice is really, really important for the climate system. And so we're using ice cores to see how sea ice has changed in the past in order to help us predict what it might do in the future. And so at the moment, we're doing quite a good job reconstructing sea ice. So this is the extent or how far the winter sea ice reaches in Antarctica. And we're comparing that to observations, satellite observations from space of sea ice. And at the moment, we're doing quite a good job. But as you can see, we really only have records from the 20th century. So there's a lot more work to do in this area. But one way to help constrain past sea ice is actually to look at biomarkers in ice cores. So this is picking up a signal of biological activity that's growing in the sea ice. And there's a number of different biomarkers that we can use. And these all have a really nice correlation with winter sea ice. So I thought I'd end on a positive. This is a pretty new and exciting avenue of research we're moving into. So to conclude, ice core perspectives from the last 800 years. So we have seen that the gas bubbles and the ice core records are really important for us to understand how climate has changed in the past. It's the only archive we actually have of the atmosphere. Over the last decade, there's been a huge amount of innovation in the way we recover ice cores, the way we analyse them, and the way we interpret the data. There's a great emergence of new proxies that show great promise. But I think in the ice core world, there are still a number of challenges. So one is interpreting these chemical records as we are rapidly advancing our analytical techniques and able to measure smaller and smaller concentrations. Also understanding post-depositional processes. And a lot of the chemistry, we're assuming that when it's deposited on the ice, it stays there. That's not always the case. Also to spatially integrate these paleoclimate records with other ice cores in Antarctica, but other types of climate archives. And then the last major challenge is archiving climate records of shrinking glaciers. So this is a project called Ice Memory, and the goal of this project is to drill ice cores from around the world, from alpine glaciers, and actually store them for future analyses. So there's some exciting work to go forward, and I think I will leave it there. stop sharing my screen.
Cool. Thanks very much for that, Holly. That's interesting stuff, and I just find the sort of the chemistry and the chemical analysis of it really, really clever. From those tiny air bubbles and the tiny section. I have a couple of questions. I don't see any questions come up on the YouTube side, but right at the start you mentioned the shallow, intermediate, and deep cores, drilling, but you didn't say how shallow and how deep. So how deep do you actually go for each of those levels?
Yes, so with that shallow drill, that can drill maybe about 10 meters, so not much, maybe going back a few decades, depending on where you are in Antarctica. The deepest ice we drill was all the way down to the bottom, so it's 3 to 4 kilometers. So it's a huge amount of ice. It can take a number of seasons to drill, working shifts round the clock. Yeah, so it's a big effort.
Is that still a 3-inch core for all the different levels?
Yes. So the usually, but actually the Americans have they have made their drills so they have quite a bigger diameter of ice, so they're getting more sample. But that's logistically challenging transporting it, etc. But typically, yes, they're around that diameter. Yeah.
And the other thing that you came up in your presentation was the event or the sudden change in atmospheric lead from Broken Hill. What happened at Broken Hill?
So I think it was just the sort of industrial revolution and the mining, and then it was transported and smelted, which released all the lead. It's just this boom and demand for minerals.
So we can't blame the Australians directly. It's the consumption of lead.
Yeah, it's a southern hemispheric pollution signal. So yeah, it's very interesting. I think we also can pick up things like bomb spikes, plutonium, and some of the other radiogenic isotopes. Microplastics are now found in sea ice. Frozen water. So really, Antarctica is feeling the pollution. Yeah.
And the other sort of crucial piece of evidence in my mind is the isotopes of carbon, because that points directly at anthropogenic sourcing of the CO2 levels. In somewhat you could call it the smoking gun, and to me that's the thing that's the clearest piece of evidence that humans are responsible. I don't see any other questions. Do you have any other comments you want to make?
Just thank you very much for listening, and if you do have any questions, I'm happy to chat further over email or phone or yeah.
Cool, thanks, Holly. I'll hand over to Linda to do the final remarks. So, Linda, it's all yours. So thanks very much, Holly. I appreciate your time, and that's been a very interesting presentation.